Welcome. Today, we're diving into the world of encryption and networks. It is all about securing your data with symmetric and asymmetric algorithms. Encryption is a fundamental aspect of network security, ensuring that your sensitive information remains confidential as it travels across networks. We will explore both symmetric and asymmetric encryption, which are two primary methods used to protect data. Let's start with the basics. What exactly is encryption? Encryption is the process of converting plaintext, which is readable data, into ciphertext, which is an unreadable format. This protects sensitive information from unauthorized access. Encryption transforms readable data into an encoded format, ensuring it is unreadable to anyone without the decryption key. A key is required to decrypt the information. This key is essential to turn the ciphertext back into its original, readable form. Encryption is essential for secure data transmission over networks, preventing eavesdropping and data breaches. It protects both the confidentiality, keeping data secret, and the integrity, ensuring data is not altered. Now let's explore symmetric encryption. Symmetric encryption uses the same key for both encrypting and decrypting data. This means that the sender and receiver must have the same secret key. This key must be shared securely between the communicating parties, as anyone with the key can both encrypt and decrypt the information. Symmetric encryption is fast and efficient, making it suitable for encrypting large volumes of data. However, it requires a secure method to exchange the key between parties. Common symmetric algorithms include Advanced Encryption Standard, Data Encryption Standard, and Triple Data Encryption Standard. Key lengths typically range from 128 to 256 bits, providing a high level of security. Symmetric encryption is commonly used in file encryption and database security to protect sensitive data at rest and in transit. Let's look at some common symmetric encryption algorithms. First, Advanced Encryption Standard, or AES, is a block cipher that processes data in 128-bit blocks. It supports key sizes of 128, 192, or 256 bits. AES replaced Data Encryption Standard, or DES, as the federal standard due to its higher security and efficiency. Next is Data Encryption Standard, or DES, and Triple Data Encryption Standard, or 3DES. Data Encryption Standard uses a 56-bit key, which is now considered insecure due to its short key length. 3DES applies Data Encryption Standard 3 times to each data block to improve security. It uses a block size of 64 bits. It is slower than Advanced Encryption Standard, but is still used in some applications. Other symmetric algorithms include Blowfish, which is a 64-bit block cipher. Twofish, which is a 128-bit block cipher. RC4, which is a stream cipher, but it is now deprecated due to security concerns. Cha-Cha-20, which is a modern stream cipher that offers excellent performance and security. Now let's dive into asymmetric encryption. Asymmetric encryption uses a pair of keys, one public and one private. Data encrypted with the public key can only be decrypted with the corresponding private key, and vice versa. This solves the key distribution problem inherent in symmetric encryption. Asymmetric encryption is more computationally intensive than symmetric encryption, making it slower for large data volumes. Common asymmetric algorithms include Rivest, Shamir, Adelman, elliptic curve cryptography, and digital signature algorithm. Key lengths typically range from 2048 to 4096 bits, providing a high level of security. Asymmetric encryption is widely used in hypertext transfer protocol secure, digital signatures, and secure key exchange to establish secure communication channels and verify data integrity. The key pair consists of a public key, which is shared openly with anyone, and is used to encrypt data or verify signatures, and a private key, which is kept secret by the owner, and is used to decrypt data or create signatures. Let's examine some common asymmetric encryption algorithms. First, Rivest-Shamir, Adelman or RSA, is based on the difficulty of factoring large prime numbers. It uses key sizes ranging from 2048 to 4096 bits. RSA is widely used for secure communications and is slower than symmetric algorithms. It is used for both encryption and digital signatures. Next is elliptic curve cryptography, or ECC, which is based on elliptic curve mathematics. It uses smaller key sizes, typically from 256 to 384 bits, while providing equivalent security strength to RSA. ECC is more efficient than RSA and has lower computational requirements. It is ideal for mobile and Internet of Things devices. Other asymmetric algorithms include digital signature algorithm, or DSA, which is used primarily for digital signatures. ElgaMal, which is based on Diffie-Hellman key exchange. Elliptic curve digital signature algorithm, or ECDSA, which is an elliptic curve version of digital signature algorithm. Edwards curve digital signature algorithm, or EDSA, which is a variant of ECDSA offering improved performance and security. Now let's explore hybrid encryption. Hybrid encryption combines the speed of symmetric encryption with the security of asymmetric encryption to create a more efficient and secure system. This approach leverages the strengths of both symmetric and asymmetric methods. Hybrid encryption encrypts data with fast symmetric algorithms, such as AES, for efficiency. It then securely exchanges the symmetric keys using asymmetric encryption, such as RSA or elliptic curve cryptography. By combining these methods, it overcomes the limitations of both approaches and provides both confidentiality and authenticity. Common applications of hybrid encryption include transport layer security or secure sockets layer for hypertext transfer protocol secure connections, pretty good privacy for secure email communication, secure messaging applications, and virtual private network protocols. Let's investigate key exchange protocols. These protocols are essential for securely exchanging encryption keys between parties. Diffie-Hellman key exchange allows two parties to securely establish a shared secret key over an insecure channel without prior shared secrets. It was the first published practical method for key exchange. It is based on the discrete logarithm problem. Diffie-Hellman is vulnerable to man-in-the-middle attacks without authentication. Another key exchange is RSA and modern protocols like transport layer security, which use asymmetric encryption to securely exchange symmetric session keys. RSA is used for secure key transport. Elliptic curve Diffie-Hellman ephemeral provides perfect forward secrecy with ephemeral keys, meaning that even if the current key is compromised, past communications remain secure. It is used in transport layer security version 1.3 and other secure communications. Now let's examine various network encryption applications. First, transport layer security or secure sockets layer, or TLS or SSL, for hypertext transfer protocol secure. It secures web browsing by encrypting data between browsers and servers. It uses a hybrid encryption approach, combining RSA or elliptic curve Diffie-Hellman ephemeral for key exchange and advanced encryption standard for data encryption. Another application is virtual private network protocols. It creates encrypted tunnels for secure remote access and privacy. Examples include Open Virtual Private Network, which uses Open Secure Sockets Layer library. Internet Protocol Security, which is a network layer encryption. WireGuard, which is a modern faster protocol. Another application is Secure Messaging, which are end-to-end encrypted communication platforms for private messaging. It includes Signal Protocol, which is double ratchet algorithm. It provides perfect forward secrecy. It is used in WhatsApp, Signal, and others. Next is Wireless Network Security, which protects wireless communications from eavesdropping and unauthorized access. It includes Wi-Fi Protected Access 3, which is simultaneous authentication of equals. It also includes Enterprise, which is 802.1x with extensible authentication protocol. Advanced Encryption Standard Counter Mode with Cipher Blockchaining Message Authentication Code Protocol for data encryption. Let's look into the future of encryption. Quantum computing poses threats to current encryption while also offering new solutions. Shor's algorithm threatens Rivest, Shamir, Adelman, and elliptic curve cryptography. As a result, post-quantum cryptography is under development. Quantum key distribution is also being developed. National Institute of Standards and Technology, or NIST, are working on standardization efforts for these technologies. Also, there are advanced encryption techniques being explored. These new approaches enable more flexible and powerful encryption capabilities. One approach is homomorphic encryption, which allows computations on encrypted data without decrypting it. Another approach is zero-knowledge proofs for privacy, blockchain-based security solutions, lightweight cryptography for Internet of Things devices. Encryption continues to evolve to meet new challenges and requirements. The balance between security, privacy, and usability remains crucial as we develop the next generation of encryption technologies. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.